gentlemen, for the day 2 virtual training on the topic on design and construction of ground improvement technology. Ladies and gentlemen, now may I invite today's first resource speaker, Mr. Govind Raj, for the presentation. Let me introduce about the speaker. Mr. Govind Raj is a practicing geotechnical engineer having 19 years of experience in analyzing, designs, and execution of foundations for infrastructure projects. He had worked for multinational organizations such as Swiss Boring, Dublin Ground Engineering, and Six Construct at various levels. He had masters in structural engineering from National Institute of Technology. Presently, he is working with Ground Engineering Private Limited since 2019 as the geotechnical manager. His area of interest includes construction of heavy foundations, specifically board piles, diaphragm walls, and deep excavations. Now I request Mr. Govind Raj to make the presentation. Over to you, sir.
Thank you. Is my screen visible?
Yes, sir.
Hi, good morning, all. The topic of my presentation is Embedded Retention Wall Design, Consequences and Measures. We all have heard about retention wall systems. They are the walls that retain material and strong enough to resist the material pressures. So the retention walls are generally divided into three categories: the gravity retaining walls, embedded retaining walls, and there is a compromise between the both systems, that is a hybrid retaining walls. Here the embedded retaining walls are mainly divided into 5 categories: sheet pile wall, king post wall, contiguous pile, secant, and diaphragm walls. Now coming to the gravity wall versus embedded walls. The stability of the gravity wall is due to the self-weight of the wall, whereas the embedded retaining walls, they penetrate below the excavation level, and the stability is ensured by the passive resistance of the soil at the base of the wall. So here we will be talking more about the embedded retaining wall only in this lecture. As per Syria C580, based on the geotechnical risk point of view, the retaining walls are generally clubbed under moderately risk. It comes under the category 2. There may be exceptions when you are constructing a retaining wall near to a tunnel, then that comes to category 3. So overall, we can say that a retaining wall belongs to the moderate risk, that is category 2. So it don't create so much trouble, but still you can see that all over the world, there are so many retaining wall failures. Now let us come to a case study. So in this picture, you can see collapse of a 13-story residential building in China in 2009. So the developer wanted to construct so many 13-story buildings. Here you can see so many here. So he didn't want to take a risk for that. He used pile as the supporting as a foundation system. So now the story of that collapsed buildings start. So they constructed the 13-story building which is resting on the piles. After the construction, he thought, okay, he wanted to construct one underground garage approximately 4.6 meter deep on one side of the building, which is comparatively very less. This 4.6 meter is actually nothing, but he wanted to construct immediately next to the building. So the excavation contractor, he made some slope and he constructed 4.6 meter and he dumped the soil on the other side of the buildings. So one way he excavated on one side of the building, other side he dumped the earth. So in effect, their pressure is increasing on the other side. And then the rain started and water started seeping into the ground, and there was loss of soil around the piles. So once the pile lost its lateral support, then it lost its lateral pile capacity and started breaking. You can see in stage number 4 and stage number 5, and the building began to tilt. And last, you can see the building on the ground. Come back to the previous slide, you can see the picture here. So here we can see that even though excavations are moderately risk category, still it can create a huge consequences. And now coming back to the embedded retaining walls, mainly they are divided into 5 to 6 categories, and the most common ones are king post wall, or we call Berlin wall or soldier pile wall. These are generally not suitable when the water table is high, and very flexible walls which attract very high deflections. We generally use soldier pile wall for maximum 5-meter excavation in a cantilever case. 4 to 5 meter, you can say, and more than that, we can still go with the anchored or with the struts. And the second category belongs to the sheet pile wall. This is also flexible, comparatively flexible systems, and you may need wailers to transfer the load mechanism. And in the dense soils, you need to have pre-drilling. The next comes to the contiguous pile walls. So here you are installing piles with a gap. Some 50 to 100 millimeter gap will be there between the piles. As compared to the first two piles, this is a more rigid system. And comparatively, the deflections are lower. Since there is no connection between the piles, you give some kind of capping beam or a railing to make it a wall. The next one, you can see the secant pile wall. Here the piles are interlocked. So with this arrangement, the water ingress can be minimized. But still there will be a lot of joints, because if I go with a 800 mm wall, maybe I go with some 800 at 700 center to center. So there will be a lot of joints in the wall. But as compared to the other types, this is a comparatively a better water retaining structure. Now coming to the diaphragm walls, as compared to the previously set systems, this is comparatively better because there will be lesser joints, and it's very is efficient water retaining wall, and it can be installed for greater depths. Even up to 100-meter, people used to construct D walls. It can carry vertical loads. Many times, especially in India, people use a D wall as part of their building systems. And it can reduce the settlement of adjacent structures, permanent walls, and the construction time for basements can be lower. There are many other systems also, but I'm just talking about the most commonly used systems. Now coming to the different excavation methods. There are two types of excavation methods. One is the top-down construction, and the second is the bottom-up construction. In the top-down construction, we construct the wall, we partially excavate it and connect with the ground floor slab and go down subsequently to the bottom. In the bottom-up,
Okay. Sorry, virtual workshops are ground improvement technologies.
Yeah, in the bottom-up construction, we use temporary props or anchors, and we go down. Then after the construction, we have to connect it with the slabs and de-stress the anchors or remove the struts. So these are the systems for the excavation. Now coming to the factors affecting the design. So These are here in the screen. You can see the different challenges in a basement wall construction. So mainly the varying soil conditions and the changing water tables and the close proximity to the plot boundary. There will be existing structures near the wall which we have to design for. There will be services. Maybe at times you will not be able to anchor it, or you will have to choose the position of your anchors according to the service lines. There will be traffic. You have to consider the surcharge. Maybe there will be some additional excavations. There may be some additional trenches near to the excavations. So these all conditions we have to address. The knowledge of the nearby structures are very much important for a retaining wall design. Generally, up to say if the wall depth is say 20 meter, it is always preferable to identify the structures which are falling in those distance and consider the effect of the surcharge in the deflection or bending moment calculations. Here you can see one building, one retaining wall collapsed due to the weight of the structures around. So the knowledge of the nearby structures are very much important for the retaining wall designs. The next one is the additional excavations. Generally, the consultant tell you a common level for excavations, but definitely there will be some additional excavations which will be close to the D wall or close to the shoring pit. Here you can see that there are some additional excavations coming near to the basement edge. Normally, if you ignore in the calculations, it can lead to the loss of stability of the walls. Also, when you are excavating, suppose you are having a 16-meter or 20-meter excavations. So you cannot always, when you excavate it, maybe the excavation will go to 20.2 or 20.3. And there can be some soft, the ground can go soft also. So in that cases, some unplanned excavation has to be considered in the design. And this is covered in almost all codes. Minimum all international codes are talking about half-meter additional excavations when you deal with the design of the retention wall systems. And the effect of the additional excavation is loss of stability, and there can be an increase in the toe moment, and there can be increase in the bending moment. In this picture, you can see a 1,000-foot tower. It is supposed to be one of the biggest biggest residential building in the Middle East. And the excavation was approximately 22 meter, very next to the creek. We all make a statement that structure is always more intelligent than the designer. It redistributes the load. So generally, even if the designer you see, even if he missed some minor points, but actually the structures are having one advantage. Even though the designer not think about it, it redistributes sometimes loads but whether it be true in all cases. So we make that story, but the story continues. Here you can see one small gap is through one area. Now the water is ingressing, and you can see the high water flow. And in no time, you can see it's completely flooded. The 22-meter excavation you can see flooded. And here the story ends. So you can see how a retaining wall can create so much serious consequences. Only you can see only the top of the crane. here what happened is they installed so many struts, but they forgot to install, not forgot, so for some reasons they didn't install one corner strut. So actually this caused the failure of this structure. And luckily there was no people didn't die in this incident, but there was a huge issues happened because of this one. All the machinery got stuck. Now let us come to the factors affecting the design of the retaining walls. First one is the method of analysis. Three common systems to calculate analyze a retaining wall. Basically, they are divided into three categories. That is limit equilibrium method, subgrade modulus method, and finite element method. The limit equilibrium method is somewhat what we make a manual calculations. You calculate the active pressure, passive pressure, then you, with the assumption of the force equilibrium or moment equilibrium, you identify the depth, you identify the prop forces and the bending moments. So here in this one, we are not actually computing the deflections. So the second method is a subgrade reaction. Here the wall is modeled as a beam and the ground as a series of horizontal springs. Then there is a finite element method, which soil structure is an elastic continuum and the soil structure interaction is there. So now out of these methods, the limit equilibrium method, it needs only the ground strength. You have to input only the phi values or c values. In fact, there is no soil structure interaction happening here. No real structural deflections are getting calculated because the wall is silent here. Only you are dealing with the pressure on active side and you are dealing with the pressure on the passive sides. Then we will get comparable results when you with the subgrade or finite element method, when we are talking about the cantilever walls or the walls or the unsupported walls. However, when it comes to the propped wall, means cantilever walls, generally you can go for some 8 meter, 9 meter depth only. But more than that, you may need supports. If you are going for a diaphragm wall, you definitely you will have to go for more supports. So in those cases, in anchored or propped cases, there will be considerable differences in the prop loads. There will be a considerable difference in the bending moments. The subgrade modulus methods and finite element methods more or less yield similar results. Even though the subgrade modulus methods are somewhat approximate, still they will give comparable results with the finite element methods. So to illustrate that, I made two calculations. One is a cantilever wall 7 meter and the second is a strutted wall. This is just for an illustration point of view. The case 1, a cantilever, and the case B, strutted or a supported wall. So in the first picture, the cantilever case, you can see more or less the comparable bending moment between the three systems. So the variation in bending moment, you can see it on only 5.5% or 6%. Not too much difference will be there for a cantilever wall. But the moment it comes with a anchored wall, the variation will increase to more than 10 to 20%. Even it will be more depending on the depth of the excavation or depending on the boundary conditions you deal with. So so the variation you can see it ranges to 30 to 35, maybe props. So when you are dealing with limit equilibrium methods are very good, very fast. You will get an approximate idea, but it cannot. You have to deal it with a whenever you are dealing with a more excavation depth 7 or 8 meters, you have to check with a finite subgrade reaction method or finite element method because the results can go drastically different in a limit equilibrium method. So the analysis method plays a major role in the behavior of the retaining wall. And now comes to the parametric study. We made some parametric study to see the influence of various parameters on the design. And the same example we are going to have a look. And here we will see what will be the influence of the water table variations, over excavations, surcharges, soil stiffness, wall flexibility, and type of the soil, untrained or untrained. So as an example, we are now dealing with the 7-meter approximate surcharge 20 and the water table on the retained side 6-meter below. So we will vary these parameters now. So this in this slide, you can see effect of water table variations, overdig impact, and surcharge impact. In the here you can see that the effect of water table variation is pretty higher than as compared to the other aspects. This water table and overdig or additional excavations create very high difference in the bending moments and in the stability. Definitely, surcharge also plays a major role, but it is as compared to the first two, you can see it's a medium impact. The same values, the same parameters, water table, overdig, surcharge, placed here to illustrate the factor of safeties. Again, you can see that the more the water table rises, the factor of safety get going less, and more excavation factor of safety going less. So these are actually considerable influence, you can say. Now there may be parameters which may or may not create. We cannot conclusively say. It all depends on again the boundary conditions of the problem. So, but overall, generally, you can say that soil stiffness and wall flexibility, they don't affect the bending moment values considerably. There can be exceptions. This is not a common rule, but still, it may not affect the retaining wall, especially the cantilever retaining wall in the bending moment area. However, they have a considerable influence in the deflections. Bending moment there may not be, but deflections definitely there will be a considerable influence on that. Yeah. Now coming to the trained and untrained behavior of the soil. Generally, when we deal with a soil, we use the untrained cohesive values and we simply make calculations. But many people make calculations, but is it really correct? Because whether there will be any problem for the by considering high cohesion values, and that also in the untrained stage, is there any issues? So to understand that, first we have to see what is the type of the soil. If it is a clay, definitely if it's a clay type of soil, and if it is very soft, generally normally we can say thumb rule here. If the soil is very soft, with the long term you will get more strength, and your critical condition may be the immediate one. So in that case, untrained analysis will be the critical, or short term analysis will be the critical. But for a stiff clay, it can lose its strength with the time, when you, especially when you deal with the retaining wall problems. So the critical method can be a trained analysis or a long-term analysis. But this is again a thumb rule, and for any type of clay, one has to deal with both the trained and untrained, consider trained and untrained parameters, because otherwise it can create to a fatal incidents. And one exercise is made here to show the difference between the both approaches. If you are making a calculation with an untrained analysis, you will end up with only 415 bending moment here in this case. And the second case, if you are going with a trained analysis, you will get a pretty higher bending moment, and you may need more embedment, and the deflections also increases in the serviceability limits. Then crack width and specifications. Many places when the in sometimes the engineer, they specify the crack width in the specification because they don't want to they want to ensure the performance in the long term. They don't want to expose more crack widths because the concrete can create cracks. So they want to put more steel and to make it a more stable structure. So this can create a huge impact in your retaining wall design. Just one small illustration. Suppose you are having a bending moment of here. I just took some example of a small uh, contiguous pile wall. So when the bending moment is 350 kilonewton meter, if there is no crack width calculations, maybe you need a reinforcement content of 90 kilogram per meter cube. With a 0.3 millimeter crack width, you are going to 105, and 0.2 millimeter crack width, you are getting a high reinforcement. So as a retaining wall designer or a D-wall designer, we have to see whether what is shown in the specifications. Whether so based on that, you have to design that accordingly. Now come to risk and mitigation plans. What are the main risk? What is a geotechnical risk? Why we want to talk too much things about this retaining wall? So definitely any ground related problem can adversely affect project cost. The cost, so basically as compared to the other systems, for example, a pile system or a ground improvement system, the retaining walls can create more trouble than any of the other geotechnical solutions because it fails in no time. It won't allow you to wait and make the repair. It may not. So so once it is failed, then it will create a huge impact for the project cost. It can create the trouble for the completion times, health and safety. The safety of the people are affected, and the quality and the fitness for purpose is affected. There will be environmental damage. So just I listed only very few points, just showing what are the risk and risk mitigation. So, the risk are okay nearby structures very close to the retaining wall. So consider the surcharge due to the building. Keep it in your design and see whether you are getting acceptable limits for the settlement and the settlements for the movements. And if the if soil data is inconsistent, if it is insufficient, don't forget to keep confirmatory soil investigation in your thing. Even though you are getting soil investigation as a geotechnical contractor, any geotechnical, it is a responsibility of any geotechnical contractor to make some confirmatory soil investigation to see whether it is in line with the tender boreholes. Then the long term and effects in clay soils. And clay soils, there is no question. You have to consider both the trained and untrained cases in your analysis. Because by conveniently forgetting one analysis step, we cannot ensure the safety. Then the over excavations near to shoring. If there are any lift pits or any additional excavation near to the as compared to the general excavation, it should be considered in the design. So that question has to be raised to the consultant before the award of the job. And the water tables higher than the soil investigation report. Generally, we cannot consider the same water table as shown in the soil investigation report. You have to budget for the increase in water table in the design. Because the water table, as we have seen in the previous slides, water table is a killer for our retention wall systems. Next, surcharge greater than the design surcharge that you have to consider in the design document. Crack width, as we told, it can increase the project cost like anything. So see the specifications, see whether it is there in the specification. If it is not there, if it's a permanent structure, ask the consultant or ask, we generally ask the client whether we have to budget for something. Now the retaining wall codes. So the common Indian and international codes are covered here. Here, mainly the Indian code 9556, we call it the code of practice for design and construction of diaphragm walls. But in reality, it is talking more towards the construction. It is giving very less guidelines for the design point of view. Very less means it is not at all a conclusive document for the design. But as compared to that, the international codes, Syria C580 or the latest version Syria C760, Eurocode 7 Geotechnical Design, BS 8002 2015. So these all gives very clear guidelines about the design point of view, whereas the Indian codes unfortunately are not really covering a very good aspect about the design. As a case study, I'm just going to show some 2-3 projects just to see a different type of retaining walls. So here I'm going to show you a 20-meter deep pit in Abu Dhabi. We all say, means previously also, even in fact, I also said the diaphragm walls are have a very good advantage over the other systems. But it's not necessary to make a conclusive statement because it all depends on the project dynamics. So here you can see that even though this is 18 to 20-meter deep pit, the secant pile walls were used because the initial thinking was to go with the diaphragm walls, but in fact that option was ruled out due to the project constraints. We will come to that constraints now. So it was 18.5 to 20-meter excavation and proximity of a some 15-story building 5 to 6 meter away. In fact, the podium structures were very close to this 1 meter away, 1 meter away only. Some B plus 3 is very 1 meter away, and the big. So why? As I told you, the initial proposal was diaphragm wall panels, but since the nearby structure is very close, 1 meter away, the podium area, the diaphragm wall panel, when you are excavating a diaphragm wall panel, say 5 to 6 meter, it exposes a large area and it can damage the existing piles. So the nearby piles were short actually. It was something like 7-8 meter long piles, whereas the excavation was 20 meter down. So the moment you excavate a 5 to 6 meter D-wall panel, there is a high chance to damage the existing piles. So another constraint was that the space was a big problem. The available space was only 850 millimeter. Definitely an ideal solution would have been an 800 thick D-wall, or if the D-wall is not practical due to this proximity to adjacent buildings, 1000 millimeters secant pile we would have thought of, but still the space was not there. And one interesting thing here, there was in one of the nearby plots, some local contractor tried for 15 meter, and it showed with I think this is also piles, secant piles, but 15 meter excavation failed and it showed excessive deflections. Another critical thing was that after the construction was started, the nearby plot owner wanted to start the shoring and excavation near to it. So it will also create problems to the shoring wall. So it is actually creating a 3-dimensional problem now because here we cannot anchor, and struts were used. Then immediately the next nearby plot, if they are going to excavate it, it is going to create an additional problems. And heavily loaded some 28-meter long unsupported were used. High water table conditions. Just you can see the nearby buildings. And even before starting the retaining wall, there was we located some cracks in the basement wall of that structures, nearby structures. So it all created some kind of alarm, and whether it's a really good project to go ahead. In the plan view, you can see the different colors which are showing the pile foundations for the adjacent structures, which I told you were close to 1 meter away and which were short. So to protect that only, we are now going with the secant pile wall. So this is the project details. So here we went with based on our past experience. Here actually the past experience helped a lot. Since we had a very good understanding of the soil in Abu Dhabi that near to that areas, we decided to go with the 820 millimeter secant pile walls. Because generally we would not take a risk, but since we are very much sure about the soil details in near to that area, we went with 820 millimeter with the two level of supports for 18 to 18.5 meter. So one advantage here was that it was after a few meters it was a rock. IGMs were coming, not rock. 6-7 meters IGM or very weak sandstones were coming. So due to this advantage, we took that advantage. Otherwise, we would not have, if it was a pure sandy soils, we would not have gone with the 820 with the two level of supports. So in order to avoid exposure to the foundation piles of the nearby buildings, only one shoring pile was drilled and concreted next to the existing piles, but other areas we made it fast, but next to the existing piles, we kept some time. After 24 hours only, in 5-meter radius, we installed only one shoring pile in a day. And the local experience had to limit the shoring size to 820 millimeter. And the design covered all critical aspects, including excavation in the nearby pit, in the safety of support systems at high temperature. Again, you can see that 28-meter is the unsupported length of the struts. There was no columns in the middle. It was all pure supported by the thick KC pipes. So this is one example of the pit which is very close to the existing building. And this shows that even though diaphragm wall is a very good system, it may not be applicable in all the cases. So the project boundaries has to be carefully evaluated. And the second case, there's a pumping station in Western India, which we 1 year back we completed. So challenge was that it's close, it's something like 100 or 150 millimeter, 150 meter to 200 meter away from the sea. So water tightness of the seawater intake structure was a problem, and there were irregular shapes. Excavation was depth of the panels were 28.5 meter deep. Cage weight was 35 tons. We lifted it in one single lift. Means we are not joining the pieces. The 28.5 meter deep and 35 tons we lifted in one single, and arranging concreting 170 meter cube per panel. And due to the high water table and changing water table, working platform created issues, trench stability and complex environment, which we completed recently. And I will show you one or two few projects which we executed some few years back. One is the TPL Lucknow Metro diaphragm wall station box. It's a top-down construction. I have already elaborated regarding the top-down construction earlier. And this is another example for Reheja D-wall system which we executed in the Chennai. Thanks all.
Thank you, sir. Thank you for making an excellent detailed presentation on embedded retention wall design, consequences, and measures. May I request to the participants if they have any questions, they may either write to us to CBIP directly, we will arrange the answer from the speaker, or they may ask right now as well.
If you have any questions later also you can share with me. We can reply to that.
Yes, the participant may write as well to the speaker or to us. We will arrange the answer from the speaker and get back to you individually over the email after getting the respective answer. Or they may ask right now as well. I believe we do not have any question right now. I guess the session is quite detailed and everything, the concept has been clear, but still if they have any question, we will definitely bother you,
Yeah, sure.
Mr. Raj, for the
Yeah,
respective answers. Thank you so much for your time. Thank you for
Thanks.
sparing your valuable time for conducting this virtual session. Thank you so much. Stay safe,
Thanks.
stay healthy. Thank
Thanks.
you. Now, ladies and gentlemen, we have the next speaker, Mr. Peter Banzev. With the permission of the speaker, shall we? Yeah, the speaker is here. Good morning, sir. Good morning. Ladies and gentlemen, now I invite next resource speaker, Mr. Peter Banzev, for the presentation. Let me introduce briefly about the speaker. Mr. Peter Banzev graduated in civil engineering from Munich University of Applied Sciences Engineering, having more than 35 years of experience in dam engineering while working at various positions at different countries. He is involved with the construction of diaphragm wall in different dam projects worldwide. He has contributed numbers of technical papers in the different conferences fora. Presently, Mr. Peter is head of dam services at Bauer Group, Germany. Now I request Mr. Peter Banzev to make the presentation. So please. So you are on mute. Kindly unmute yourself.
Mute. Yes, now I was successful to unmute. Good day to all of you. I'm just working to start the presentation. The presentation should be on right now.
Yes, it is visible.
Perfect. Yeah, thank you for the introduction. A good day to all of you in India from Germany. It's something we learned throughout these years of COVID pandemic to have video conferences around the globe. and not be virtually present. Well, also I enjoyed every time I was there in India to have a presentation in India. But with this measure of video conferencing, it's working also well and fine. The introduction was given already. I'm working with this Bauer company for almost 40 years. And just a few words about the Bauer Group, Bauer company. The Bauer Group is a special engineering company, a special engineering group. Building equipment has a strong arm for the construction and also is venturing into resources. The construction company, the Bauer Spezialtiefbau, has more than 40 companies around the globe, one of which is Bauer Engineering India Private Limited. Mr. Dr. Bandi will give a presentation today from our company there. Colleague I admire a lot. Right. For my presentation covering a wide range of themes of topics, pile foundation, diaphragm wall, slurry wall, mixed in place wall, and I'm ending with a dam project, a rehabilitation project, coming then also to question and answers. In the previous presentation of Mr. Govindraj, he stressed it already a lot that geological investigations are the key to success. It's also my point, my aspect that you have to have a proper geological investigation and proper testing to have the basis for a good design, and a good design is the basis for a proper execution of such projects, for the safety of the structures nearby, for the durability of the building as such. And I just highlighted here a few aspects for the design which are important from my point of view. Talking about the diaphragm walls, talking about it also applies to secant pile walls, as just very well covered by Govindraj in the previous presentation. You need to be aware of all the load cases. You need to be aware of the construction process. Maybe a top-down construction as shown here. You need to have several steps. Also, these need to be covered. You need, and he mentioned this from this Abu Dhabi project, you need to be aware of your neighboring buildings, how these buildings are found, whether they are on raft foundation, on pile foundation. You need to be aware whether these previous buildings have a basement. A basement could mean that tieback anchors are in the vicinity of your new building, your new structure. You have to be aware of the utilities around your future excavation pit. All this has an effect on the design. All this has an effect on the execution. When it comes to barrier walls, to diaphragm walls, cut-off walls in dams, there are similar points, but also some differences. Again, geology, I stress this, and Govindraj also mentioned the Eurocode 7. This is also for us typically the basis. Also, there are good standards and codes in India as well. For a dam, important is the situation for an embankment dam. You need to consider settlement of this dam. If you have a new dam, cut-off wall under a dam, as shown here in the sketch, under the core of the dam, you need to be aware that the new dam is settling for some time. Also, these loads have to be taken into consideration when you make a design. Seismic, typically for dams, is much more an issue than for excavation pits, than for structures. So these are specialties for cut-off walls, specialties for designs for barrier walls for dams. And for piles, similar again, geology is very important, load cases, and the foundation, the depths of these piles. You need to be aware of possible lateral loads to these piles, not only the loads on vertical loads, the lateral loads, depending on the geology. You have to take into consideration maybe for the design loads from the soil, negative skin friction. These are aspects. And then, of course, for piles and for the structure on top are the settlements. I'm coming to this, how to prevent settlements, what to do best for settlements. So this is the start of all. Have a good geological investigation, have a good design. You need then to take care about your material. This is just an overview of Dremmy concrete. There are good guidelines for Dremmy concrete. One is shown here, the guide to Dremmy concrete from Deep Foundations. This is EFFC in Germany and DFI, covering the topic of concrete. I'd like to stress only one from this sketch here, one important point. I'm coming to this later in the presentation as well. The workability of the concrete. So there are the ingredients, there are the properties, there's the characteristic of the concrete, everything's fine. But the workability of the concrete is very important for the execution. For a contractor like a Bauer, when you have elements, long elements, large elements, workability for the entire time of the execution of the concrete pour is important. It's not only the slump, the initial slump you may test when the concrete truck arrives on site, but you need to be aware that the concrete has to be flowable for the entire duration of casting an element, of casting a D-wall panel, of casting a pile. For concrete, for dams, we typically use so-called plastic concrete. Most of you are aware of plastic concrete. Plastic concrete is a more ductile concrete. It's a concrete where we adding typically bentonite. And this bentonite gives a certain ductility. The strength is much lower than a structural concrete. So here in this example, we have a strength after 7 days of 1.8 megapascal, after 56 days of 2.8 megapascal. This is the typical range of strengths of plastic concrete or earth concrete. With the E modulus, depending on how you measure the E modulus, could be in a range between 750 and 1,200 megapascal. So geological investigation, design, the material you're adding to your elements, important to start, and then the construction. With several aspects when we talk about D-walls, when we talk about piles, one of which is the excavation pits, was covered in the previous presentation with the secant pile wall. For deeper excavation pits, we typically install D-walls. Then also if you have tunnels or you have very deep basements, you may need, depending on the geology, depending on the water table, you need to make a slab underneath, a grouted slab, for example. And depending on the depths of the slab, you may need, if you have a high slab, you may need to add piles to prevent an uplift of such a slab when you're excavating your excavation pit. An example here for D-walls, quite a large number of D-walls. Bauer installed a number of D-walls for for the stations, for the metro in Cairo. It was very congested, and this was what we did there. We installed D-wall panels to the required depths. We installed slabs there because the water table in Cairo is quite high. This is almost all sandy material. So we installed soft gel slabs, plugs, not jet grouting. Could do it with jet grouting as well, but soft gel is a quite economic solution. And for some of these excavation pits, for the stations, when the station is relatively wide, then we installed king posts. King posts just to support the top-down construction, to support the top slab when you're excavating underneath, or the middle slab when you're excavating further down. So D-walls, king posts, slab, or a plug. This is the typical construction for such excavation pits for stations in Cairo. Here, the boring machine for the tunnel is just entering this station. Foundations, piling for foundations. There are several reasons to install piles. A few are shown here. Bridges, other superstructures may be put on piles, but typically are the buildings put on piles, high-rise buildings here. And all this high-rise building, the tallest high-rise buildings these days on Earth, which are not found on rock, are found on bower piles. This is a sketch of the Burj Khalifa in Dubai, which is about 880 meters tall, is resting on bower piles. Or the Kingdom Tower in Jeddah. Kingdom Tower is under construction, will have a height of more than 1 kilometer, more than 1,000 meters. The tallest building in Germany, in Europe, the Lakta Tower in Russia and St. Petersburg. All of this are on piles, on bower piles. Apart from other structures, it's not only the towers, but here a bridge foundation. Just a picture of the Hong Kong-Macau Bridge Foundation. I have more details on this one as well. But interesting here for this part was that the foundation was not on sound ground, but it was on barges on the sea. There are different types of piles. We have the Kelly piles. Kelly piles are by rotary drilling rigs, typically cased, partially cased, or fully cased, with temporary casing, with permanent casing. The advantage of this piling method is the diameter. With big rigs, you could have pile diameters of 2 meters, 3 meters, and more, and the depths. With the Kelly system, such piles are installed, and they have an example on this of more than 120 meters. Other techniques are rotary techniques, continuous flight auger piles. These are piles without a casing, so the soil is supported by the soil which is on the flight of the auger. And when the augers reach the final depths, you're concreting through the stem of the auger, and you're installing by this way a pile. A very fast method, as you're just drilling your auger down once and then concreting, and you have a pile. Very fast method. Also, this pile, depending on the concrete, could be reinforced after the pile is concreted. If you have a very soft soil, and the method, the soil on the auger is not able to support the soil fully or safely, you could have the similar system, continuous flight auger system, with a casing, which is called double rotary system. So you have a casing outside, a temporary casing outside and the auger inside. You could also fast method to install the piles. The disadvantage, the depth of these piles is limited to the length of the auger. Depending on the rig, you have depths of 20 meters, 30 meters at maximum, I'd say. A very special feature is a full displacement pile. Also for foundations, this full displacement pile is improving the soil while you're installing, while you're drilling down. This is such a typical displacement boring tool. So you are drilling down, you're displacing the soil laterally, and this will give you a better load bearing of your piles. Another advantage is it's not only a fast method, it's limit to the length of your drilling tool, of course. But the advantage is you have almost no excavation, no material to be carved away. And for in area where you have a contaminated soil, maybe this is one aspect you would like to consider. Just you have almost no spoil with this method. Fast method, economic method, is a method to improve the soil while you are installing the pile. You have a better load bearing with these piles, and you have almost no spoil. So this may be advantages which you would like to consider when you're planning such a pile or pile foundation. Another possibility to improve the load bearing of piles is post-grouting or skin grouting. Now, what is this? If a pile concrete is installed, and then after the concrete has is hardened, then you are grouting through pipes, and you're just forcing cement grout between the skin of the piles and the soil. This will compact the soil with typically sandy soil, and this will increase considerably, depending on the pressure, depending on the geology. This will considerably improve the bearing capacity of these piles. So for this example, we improved the soil here, the sandy soil, in a way that we could save 22% of the pile length. So this is another aspect to have economic solutions for piling to be taken into consideration. Another one is so-called end bearing grouting. We are using lift cells for this. So this is a steel element, and when the pile is cast, when the concrete starts setting, then we are concreting these elements and sort of just putting the entire pile under stress. And this will improve the tow resistance of the piles. So depending on your geology, when you say, okay, tow resistance need to be improved, this could be a method to improve tow resistance of a pile foundation. And all of this, you need to test the piles. Of course, there are several number of pile tests. What I like to stress here is that I recommend, if you have a construction with a significant number of piles, do pile tests in advance. Well, this will help the design. This will save on money. This will just see how this pile could be installed in a proper way, in a better way. So don't save the money up front, save the money for the project, do some pile tests up front, and you see how the piles will behave, and you also could optimize the piles. There are several types of pile testing. I don't, here in this short period of time, I'm not going to all of these details of pile testing. Now, I mentioned this earlier, of a very specific pile installation. We installed Kelly piles here with the rotary drilling rigs, and this is the foundation for this Hong Kong-Zhuhai Macau bridge I mentioned earlier. We installed the piles from barges. Here, twin excavation of with two drilling rigs. These are the drilling rigs, these large rotary drilling rigs on barges. All of the setup had to be on barges. In the sea, down to the sea level, we installed permanent casings, and inside of the permanent casings, we drilled down with slurry support to the final depths of the pile. The slurry had to be in silos here, also in barges. The reinforcement cages had to be brought by barges, lifted into the piles. The concrete was brought by barges to the locations. Even the spoil here, the spoil was brought away by barges from the locations of the pile foundations. Very challenging project, interesting project, and a successful project. The piers are all installed, and even the bridge is now installed and is working and functioning quite well. Interesting project. On a smaller scale, also from barges, from smaller barges, we could do pile foundation in rivers. This is in the Pasig River in Manila. Also there, we're building a new bridge, designing a new bridge. We installed from barges here piles in the Pasig River. And by now, the piers are installed and the bridges started to be built. Such a rotary drilling rig, I mentioned earlier, they have a diameter of pile 2.5, more than 3 meters if necessary. Sorry, and the pile depth is not really limited. For the large rig, this is the largest rotary drilling rig on Earth, built by Bauer. We installed piles in Kuala Lumpur for the KLCC Lot LMN, and down to more than 120 meters. For the podium, we had pile diameter of 2 meters, and for the tower, we had pile diameters of 2.5 meters. This is the site impression. The piles were installed with a temporary starter casing and then drilled down to the final depths with the slurry support. Just an impression, there's the Petronas Towers you may know from Kuala Lumpur. It was just next to it. Just a few data on this pile foundation. The cage weight was 70 ton, which is quite a strong, large case. We had also, for the podium, we had to install some king posts, also very heavy king posts. The deepest pile was more than 121 meters, and the concrete volume for such a pile is almost 540 cubic meter. 540 cubic meter concrete to cast concrete. It takes time. I mentioned about this earlier, that you have to be aware of workability, of flowability of such pile concrete for quite some time. And here, to cast such a volume, depending on availability of the concrete trucks and so on, we had time of we're casting 40 to maximum 70 cubic meter an hour. So if an average 50 cubic meter for such a pile, you are casting about 10 hours. The cage installation took a similar time. Just a few impressions about the site. The casing installation, this is that temporary casing on top, just a starter casing. Then with this large drilling rig drilling down to final depths, more than 120 meters. Important is here as well that you have good knowledge about the verticality of your pile. You have several methods to measure the verticality of such a pile. There's sonic methods like the Coton testing or the sonic caliper testing. We had both of these features on site, and we're checking against each other for both of these typically good results, showing the verticality, showing the pile installation on top, the casing part, and then further down, almost no caving in was a very good pile. Heavy reinforcement installation. As mentioned earlier, this took quite some time because this were segments of reinforcement cages. And for this large volume of concrete, which were installed by typically Tremie Concrete, a large fleet of concrete trucks concreting such piles. King post installation. This is such a typical king post. As in the sketch earlier for the project in Cairo, we also installed similar king posts for the height of the excavation pit to support the slabs. Also here for the podium for the project top-down method for the podium, we supported the slabs with such king posts. You need to install the king posts very accurately. They are the future columns of the building here of the podium. Now to cut-off walls for dams or for other structures. We are installing cut-off walls for dikes and for dams for existing dams or dikes from the rest of the structures, just to improve the structure, to rehabilitate the structure, to install for dams a new core when the aging core is seeping, or for new dams, typically you're installing such elements underneath the central core from the foundation level, or if you don't have a core, if you have just a concrete face covering of this, then the element of this wall would be in front of the dam toe. But not only for piles, this is a project in Jordan where we installed a cut-off wall, a diaphragm wall, type cut-off wall next to these brine ponds. The Arab potash company is using these brine ponds here, and they had seepage issues. The brine was seeping underneath the dikes, and the Bauer was tasked for several kilometers to install new cut-off elements. We install this by grab typically, and then to the final depths with a cutter. And due to the brine, which is then also damaging concrete after some time. So in the concrete elements, we installed then in the fresh concrete elements sheet piles. So this was a combination, a hybrid combination of wall. You had a concrete wall, and inside you had sheet piles. So these are just some impressions about where such cut-off walls or diaphragm walls are installed. You could install the circular elements also for shafts. Here for the Ismailia tunnel, these are the new tunnels under the Suez Canal. We installed the starting shafts on both sides, huge circular shafts there with diaphragm wall technique. The excavation pit for the Opera Parken was also installed by grab and by cutter. This is a permanent feature. The wall here, the outer wall of this excavation. This is then incorporated in the building. And for such walls, you would need typically stop-end technique just to install rubber elements to have a better sealing in the joints. This is for such elements, for such excavation pit elements, for building structures, you would install with stop-end technique such rubber elements, such sealing elements. This steel element is you just install this the sealing element, and then this panel will be taken out when you have this is installed together with a primary element, with a primary panel. And when you're then excavating the secondary panel, you're just taking the steel element out, and the rubber element, the sealing element remains. For slurry walls or for cut-off walls for piles, you will not install typically reinforcement, no reinforcement, and also no sealing elements. But for slurry walls, you may install also sheet piles in such a slurry wall to have a permanent feature, a permanent cut-off element with just adding to this the softer material of slurry, of bentonite slurry for such walls. Slurry walls, just a special feature, could be installed in a very cheap way, but to limited depths by such long reach excavators. This is, yeah, for some temporary use, I would say recommendable if you have permanent features under dikes, permanent features under dams. The quality control here is limited. So it's an economic method. It's for temporary use. It's good to limit depths. It's good, but for duration, for longer duration, for dams, for dikes, I would not use this. Contrary to this, also quite an economic method are typically the mixed in place method or cutter soil mixing methods. The mixed in place method with triple auger technique is something which may be new. I have a short film here. I tried to open the film. Let's see whether this works. Right. This is the mixed in place technique with a triple auger, as Bauer uses this for dikes, typically since more than 20 years, almost 30 years, as durable elements on dikes. But also we are using this typically now for dams, depending on the soils. For settled dam areas, we installed this already as a permanent feature for a dam, such mixed in place walls. So this is something which is could be an interesting aspect when you have a rehabilitation of a dike, when you have a rehabilitation of a settled dam area of an embankment dam. This could be a technique, an economic technique to be used. The depth, but is limited. The depth is limited to, depending on the rig size, to the range of 20 meter, almost 25 meter. Bauer is starting to build rigs now to have such a feature down to 30 meter, 30 meter. But as I said, the depth of this economic and fast method is limited. Another mixing method is the cutter soil mixing method. It's a bit different from the triple auger. It was developed out of the cutter technique. Just a short video here as well, and I will interrupt this video as it's also covering mixing techniques, so I will not show all of it. It's just music because I'm turning it down a bit. The setup is similar to the triple auger. You have a mixing plant where you're mixing your slurry, your bentonite cement slurry. You have a starter trench, and this is the cutter technique, which is modified to be used as cutter mixing technique. The mixing is with the wheels, and you're adding then while passing down, you're adding the cement bentonite slurry to mix. Turning the music a bit more down. You're adding while going down and mixing the cement bentonite slurry with the soil. The advantage is that you could also, with this technique, you could also enter or just cut into softer rock. So if you have a good embedment of such a wall in stronger, in harder material. Also for this, you could install then steel elements if required. And I'm showing you an example where it was required to install in such a dike or in such a wall steel elements. Such walls are used for excavation pits as well, and for excavation pits, so we are using steel elements, just less deflection, or you have then elements where you install your tie-back anchors through the elements. Similar to the diaphragm wall technique, you have primary elements, secondary elements. The secondary elements are cutting into the primary elements and giving you then the continuous wall. Okay, this is. So primary elements, secondary elements reinforced where needed. This will give you a continuous retaining wall or a continuous cut-off wall. We're using this on several features for excavation pits. I mentioned this for dikes or for dams. Now to this special feature where we used and needed a reinforced mixed in place wall. This is a dike for a dike in the southern part of Germany along the river Iller. And the dike need to be rehabilitated, need to be improved. A new sealing element, a new cutoff element had to be installed. And the design asked for a higher dike, just to accommodate for future higher floods, higher precipitation. The problem here was for the planner that the area was not available to build a higher dike. Then it was decided to build an element in the dike that the dike could be overtopped. Typically, if a dike or a dam is overtopped by water, it's flushed away, it's damaged, it could be a fatal damage. But if you have a strong element here and a reinforced element, as we installed it here, we with the spilling over, and this just happened a few months after the wall was installed, we were uncertain whether this bentonite cement mix already had enough strength, but it worked quite well. So this is the river Iller behind the wall. This is the view, the past dam. This is the downstream side of the dam. It was just a spillover of some water, but not the entire river damaged the city of Sonthofen or the nearby village. So this is something to have in mind. Such reinforcement elements mixed in place walls is possible, and it's working quite well. Now finally to a real dam project. One of the almost 40 or more than 40 concrete cut-off walls which Bauer installed around the globe for dams. The Roshaupten Dam rehabilitation. Rehabilitation is more and more a topic for Bauer and also for the planning engineers, for the authorities to take care about the dams. Also in India, I know that dam safety is a big topic now, that the dams are checked, the dams are controlled, and some of the dams and the machines at the dams, some of the dams have to be rehabilitated. And this is a way to rehabilitate such an embankment dam. The Roshaupten Dam is just a dam at the Forgensee. Is the river Lech is impounded here. And it needed to be installed quite fast. So we worked there during summer, but also during winter season on this dam. This dam rehabilitation, the dams are typically partially impounded. So this is another point which you have to be very careful with your design. Partially impounded dam and the behavior of this dam while you're installing a wall with heavy equipment on such a dam. A design issue which has to be taken care. The embankment dam built in the early 50s had a core, and the problem here with the dam was that it's built on a karstic feature, so we had some seepage in the karst, and the seepage in the karst started to damage already. The embankment started already to damage the core of the dam, and it was was urgent to take action here for the safety of the dam. The first step was to install some grouting, to do some grouting on the southern side or on the left abutment of the dam. There we had this seepage issue in the karst. We also had this damage, some bigger features already which need to be grouted, which need to be pre-treated to install the concrete cut-off wall, the plastic concrete cut-off wall safely, and with this concrete cut-off wall to install at the end a new core down to 70 meters in this dam for the entire length of the dam. Pre-treatment is an issue. Pre-treatment is an issue here in such a situation. Pre-treatment is also an issue when we installing dams in the Himalaya area, where you have in your valleys where you have alluvium, colluvial material, which is not really able to sustain, to support a trench, to support the slurry in the trench. So to be sure to keep the slurry in the trench, you would need to do a pre-treatment. We did it in for some dams in the Himalaya already, Dauliganga, but also here in this case, we had to do a pre-treatment before. This was on the south side or on the right side of the dam. Some rock grouting and some TAM grouting, the tuber-manchette grouting in the dam area itself, sleeve pipe grouting called as well. By now, you're monitoring your grouting. You know exactly where your drilling rods are. You know exactly where the openings are for your grout. You know the volume of grouting, and this is some data you will have readily available on almost daily basis, not only on daily basis, but on hourly basis. When you install such an element, when you're grouting, you have this immediately on your screen. Another interesting feature here was that as we had some coarse material here on top of the dike, typically you have a cut-off wall. You have a cut-off wall here for this for the top of your element, of your top of your diaphragm wall, a guide wall, and the guide wall here had to be extended because we had some softer part here. We had some coarse material here, and we were not sure whether this coarse material of the dam was able to sustain, to cover the slurry when we were excavating for the diaphragm wall. So we installed mixed in place with this triple auger mixing. We installed mixed in place elements as so-called encasement wall. So on the upstream, downstream side of the future cut-off wall, we installed first the mixed in place wall. Then on top of the mixed in place wall, the guide wall, and then with the guide wall, I can hardly see the mixed in place wall underneath. Then on top of the mixed in place wall, the guide wall. So this was an encasement wall just to make sure that the slurry will not flow away. Even you could do this for bigger depths. We did this in the US down to 60 meters, such encasement walls, because there the risk was in karstic feature underneath that the slurry will be lost in cavities. So such encasement walls for special features may be useful for dams. I'm talking about dam rehabilitation. I'm talking about, have in mind, impounded dams. So this we have to be very careful what design to follow and what elements to install to have a safe installation of the cut-off wall. This is the triple auger mixing, just installing this encasement wall up front before we installed the final wall. The other interesting feature is just to go back here to that we have a very narrow working platform. In the past, for such big machines, you had a working platform of 20 meter, 30 meter width. We learned by now to install such a cut-off wall to 70 meter and more from relatively narrow working platforms. The width of the working platform was just 13 meter, 13 meter. And with these big machines, such a big machine here on the very narrow working platform, have in mind you have to check your dam before whether the dam is able to to sustain the load of such a cutter. On this very narrow working platform, another task was to have a proper sequence. And the sequence for such projects are with computer aided. They are just not only carefully monitored, but they are planned on a daily basis which equipment has to move how and when. So this this wall was installed, primary elements, secondary elements, with grab, with cutter and a service crane on this very narrow working platform of 13 meters. And the sequence was properly planned, which equipment had to be at what time, at which element. How to install on such a dike a wall. I have another short film here for the installation of the diaphragm wall, the cutoff wall for this dam. You will find these films also in the internet. We have on a YouTube, you have a Bauer YouTube channel, and there you can also see and just again look at these films and these animations. Step one, top part excavation by grab. We use the hydraulic grab. Also, the grabs are now equipped with the flaps to steer the excavation, to steer the grab is excavating here. Grab excavation is a fast method. It's a cheap method. Contrary to the cutter, cutter is more expensive excavation with a cutter. So the first part typically is done with the grab, just to save money, save time. And then you're coming back to cutting down to the final depths with a cutter, and you will install the secondary elements with a cutter to have the overlap. This is the guide frame, temporary guide frame. The advantage of such cutter is that you can cut in soil, but with it, depending on the teeth setup, you could also cut into rock. And this is very important for such walls to have a good embedment in rock. This is the main reason often when you install a new core in for such a dam rehabilitation, that you have the core embedded in rock. This is the steering of the cutter. We have 12 steering plates here, and the operator sees exactly where the cutter is in the ground and can steer the cutter. Slurry, you need slurry to support temporarily the drench. We use bentonite slurry or polymer slurry. Here in this case, we used bentonite slurry. You have descending plants, big descending plants on site, just to descend the slurry, to reuse this slurry, and to separate the cuttings from the slurry. You're using such descending plants, screening the bigger parts, desilters, cyclones for the small parts. Right. And after you've cleaned your trench, you've clean, good quality of a slurry, you will install your tremie pipe, and then you will concrete your elements. Concrete with the tremie technique from bottom up. The concrete will just push out the slurry. There are pumps here on top just to suck away the slurry. And this is the way to concrete such an element. Diaphragm wall technique, install primary elements first, and then cut into the primary elements. As I said, for such cut-off walls, you will not install reinforcement. You would not install rubber elements for sealing. When you do a proper job here with your overcutting, this the surface is that surrounded that you cannot see visually that there is a joint. If you have a good job, then you will not see where is the joint between the primary and the secondary element. Right. This is the installation of for this resultant dam. The typical installation for dams when you install cut-off walls with diaphragm wall techniques for these dams. An impression for in the winter season is that we are working in winter as well to install in relatively short time the cut-off wall here for the project. And just the key takeaways for me for such a dam rehabilitation is that this is by now the experience is available that you can install safely new cores in embankment dams, in impounded dams. Is it a typical thing you have to take care in the design? Pre-treatment, I mentioned this. Pre-treatment is state of the art these days. This is standard. We are using the pre-treatment, as I said, in alluvial, colluvial material or in such karstic features. Important is that you have that you contain your slurry in your trench when you're excavating. Loss of slurry is a risk for such installation in an impounded dam. And if you cannot accommodate the risk with pre-treatment, with grouting, you would go for an encasement wall. I mentioned this earlier, encasement wall, there are different types of encasement wall, mixed in place walls, also concrete walls. So either pre-treatment by grouting or if it's required, an encasement wall. Limited working space for dam rehabilitation. This is often an issue. You don't have a wide working space. This is possible to have these big machines on a relatively small working place. This is to be kept in mind. And another feature not shown here, we did it on other projects. You have often for dam rehabilitation, you have combination of concrete elements, a concrete part of the dam and an embankment part. And when you install a new cut-off wall in the embankment, you need to connect your cut-off wall, your concrete wall, to the concrete part of the dam. Also, this is possible. We did this on other projects. This is a separate presentation, maybe. But also this is possible to connect concrete elements, to connect the cut-off wall, a diaphragm wall, into a concrete dam. Yeah. Different type of methods, different type of how to install walls. You could install walls with piling technique, as shown in the previous presentation, secant pile walls. We are using secant pile walls as cut-off elements for smaller dams, for smaller dam rehabilitation could be used, but typically you would use grab and cutter concrete diaphragm wall technique, or you could use for the settle dam part here. This was not required here, but for the settle dam part, you could use mixed in place, a cheaper, faster technique. Yeah, this is covering the diaphragm walls, covering piling in a very short, condensed presentation for you. I'm happy to take your questions. And I'll just highlight for more information, there are a number of links for websites, the Bauer website, Bauer India website, the website for our dam knowledge. I've mentioned about the YouTube channel already, and there are some documentation, some brochures, more on the techniques I just touched here briefly. This is the end of my presentation. I'd like to thank you for listening, and I'm happy to take questions if you have questions right now. If not, here you will find my web address, my email address. I'm happy to answer questions later on as well. That's it from my side, and that's it for now. Thank you very much.
Thank you, sir. Thank you for making an excellent detailed presentation on design and construction of diaphragm wall, slurry wall, piles foundation. May I now request to the participants, if they have any question, they may ask.
Yeah,
Right.
I have some questions, madam. Kindly, are you audible? Might is audible?
Yes, you are audible, sir.
Yeah. My question is that once the diaphragm wall is constructed as a cut-off wall in dam, how it will check its integrity? This is first question. Second, if joints are not connected properly under the ground, then how it will be rectified? Okay. Then third is it allowed to flow the water if quantity of seepage is permitted? These are my three questions. Kindly explain, sir. I am referring this in contrast of Polavaram project.
Sorry, you're referring to the Polavaram project.
Yeah.
Right. Integrity of walls are typically checked while you're installing your wall. If you have a defined area where you install your wall, if you have defined concrete quality, then you're defining already the quality of your wall. On top of that, you would then, in some cases, you would also then go for coring, take cores from the wall just to be sure about the quality of the concrete in the wall. But typically, do a proper design, do a proper mix design of your concrete, install your concrete properly, and control where you install your wall. You have we are checking the excavation. We are visualizing the excavation, so you know where you're installing your wall. You know the connection between. You have the overlap. These are things which are controlled on an hourly basis, on a daily basis, and visualized by computer. But on top of that, if required, if you like to have more on the integrity of your wall, you would go for some coring. Joint rectification. To rectify joints, this is, you're referring to the Polavaram. There's, to my knowledge, no particular issue with the joint. We had another issue in Polavaram where the wall was not covered properly during a monsoon season, and some of the top part of the wall was damaged. But how to cover this, how to rework a joint in such a wall, you would install a new wall on the upstream side, adjacent to the existing wall with a cutter technique, and then you have perpendicular to your elements attached or adjacent to your original wall, your particular perpendicular element cutting into your existing primary wall to have another feature, a new wall behind your existing wall. And then the third question, that was not really sure whether I answered the third question about seepage. Could you please repeat your third question? Looks like gentleman's not here anymore.
Can you please repeat your third question?
About seepage. You had a third question about seepage. Okay, if the question comes up later on, please send me an email and I will be happy to answer the question.
Sure. Participants may kindly write to us or to the speaker directly. We will arrange your respective answer after getting the answer from the speaker, and we'll get back to you over the email.
Just a question: is the presentation? It's is the presentation available also as PDF for the audience?
But we don't have the PDF version of your presentation, sir. It's not been shared.
I did send it this morning. Sorry.
Okay, you already sent it this morning. I didn't check today's email. Okay, then it's perfectly fine. On the PDF version, we will definitely going to share the PDF version of the presentation to the participants. Thank you, sir. Thank you so much for your valuable time.
Thanks a lot.
And conducting this session, virtual session. Thanks to all the participants. Special thanks to the speaker, Mr. Peter. And we will now take a break for the lunch and reassemble at 1500 hours. Thank you all. Stay safe, stay healthy. Have a good day.
Thank you. With you.
Thank you, sir. Thanks.